Hey, this is Mr. J. Let's talk about coordinate geometry proofs. There's a lot of different types of figures that we can use to do proofs. We can do right triangles, we can do isosceles triangles, we can do rectangles, squares, rhombuses, parallelograms. We'll talk about that in just a moment over here, other types of quadrilaterals and stuff like that. But what we're going to do is we're going to focus on the rectangle here and what I'm going to call the parent parallelogram down here. Okay, so let's come over here and let's look at the parent parallelogram family tree. So let me just blow this up some so we can talk about this. All right, so at the very top you have what I call the parent parallelogram. All this is a family tree, so that means as you go down through the parallelogram family tree, that this rhombus and this rectangle are going to inherit all the properties from above, and then it might add some things. And then the same thing here and everything. The square is going to inherit some properties from everything above, and it might add something as well and everything. Actually, what's going to happen here with the square, we'll see it's got all the properties of the three other types of parallelograms. So the main definition of a parallelogram is a four-sided quadrilateral that has opposite sides that are parallel, right? Like that right there, double parallel symbols. The opposite sides have got to be congruent, right? So again, all of these properties flow down through all four of these. Let me go ahead and put this here, there with the rhombus. All four sides are congruent, right? Same thing down here, my bad, like that right there. And then what you also have, of course, is we're not going to use it too much in this unit and everything, but you got opposite angles are congruent, right? And the thing we're going to focus on is are the diagonals here. Okay, so the diagonals, they bisect each other, which means that they cut each other in half. In this case right here, the segments of this diagonal get cut in half, so those are congruent, and then these right here are congruent like that right there. Now, all four segments aren't the same length, but you have two pairs that are. Okay, so that's all the properties of the parent parallelogram. So that means that the rectangle has all those properties. The big differentiator here is that in a rectangle, if we can prove that the diagonals are congruent, right, so we're going to go congruent here, then that means that it's going to be a rectangle versus a parallelogram. So we'll do this down here in a moment with the distance formula with the example over on the left that you saw just a moment ago. And again, up here, we're going to use this right here as the midpoint formula as our method of proof. Now, granted, down here in the rectangle, the diagonals bisect each other and everything, so we can use the midpoint. So this isn't perfect. This is just kind of like a quick and dirty thing that the EOCT, the documentation we have and everything as teachers of geometry seem to focus that they want you to be able to do a straightforward proof of between these two types of parallelograms, one with the distance formula with the rectangles because the diagonals are congruent, so it lends itself very well for doing the distance formula, and up here the parallelogram with the midpoint. Okay, so down here, what is added with the rhombus? Well, the thing that's added here is that those diagonals that are perpendicular. So we get that down here as well. And of course the square, it gets everything. It has parallel sides, congruent sides, it's got congruent diagonals, and it's got these diagonals that intersect at perpendicular angle. All right, so let's transition from that. Let's come over here. That's the properties, and let's talk about what we can do here. Well, if we're going to do the distance formula here and prove that this is a rectangle, then we need to figure out what the components are and everything. We know that a rectangle is supposed to have right angles, so we can say that right there should be a right angle. But now then we want to focus on the components that make up this right triangle in here. So where we're at, we're going from 5 to -3, so what's that? So change in y of 8. We're going from -6 over here to 5, so 5 plus 6, or 6 plus 5 is 11. So that means that these components up here, AB and DC, should be the exact same lengths. All right, so let's go over here and do this with our distance formula. So let's find the distance. Let's find the distance of AC first. So that diagonal AC, let's go in here, the square root. All right, so the change in X is 11. So we're going to do 11 squared, and then change in Y is 8. We'll do 8 squared. And then what have we got there? 121 plus 64, which is equal to the square root of 185. Okay, I think square root of 185 is simplest form, but we could check that if we want to do a factor tree, or we could turn it into a decimal. But let's just leave it like that right there for now. Well, we can see that quickly that if we go find the length of dB, that diagonal, that we're going to have the exact same thing, right? It has the exact same components. So you're still going to have 11 squared plus 8 squared, which is the square root of 185, excuse me. So we have verified that these lengths are the same length. All right, so that means that we know that it is a rectangle versus a parallelogram. All right, so that's what we're trying to do. We're trying to figure out between two figures proving geometrically. And you could write a statement that says, I know that this is a rectangle because the diagonals are congruent and they equal this measure here in square root of 185 units. And again, you could talk about how you could go find the slope between A, B, and DC. What is that going to be? The slope is going to be, there's going to be no slope because they're horizontal lines, and you can find that BC and AD are going to be undefined slope because they're perfectly vertical lines, and that would mean that they're parallel. Okay, so let's move down here to the parallelogram. So I've already gotten the points written here, and we said we're going to focus on the midpoint formula. So the midpoint formula, if you remember, is nothing more than adding the x's, right, and dividing by 2. So we're averaging, adding the y's, and dividing by 2. Right, so we're just averaging. So let's go do that. We'll start out with AC. So the midpoint of AC is equal to, what have you got? -3 plus 2 divided by 2. Right, that's that and that. Now then we're going to go with the 3 minus 2 divided by 2, which is this and that. We'll close that off here. -3 plus 2 is -1, and then we divide by 2, so we get -1/2, and there we get +1/2. Okay, so all right, so that looks good. So apparently the midpoint is at -1/2. Let's check that. Sure enough, yep, looks like that right there would be that right there. All right, let's just verify real quick that it's going to turn out to be the same thing for diagonal dB. So let's do dB here. All right, and if I get some different answer, then I've got to go back and check maybe the points that I wrote down or something. All right, so here we go. What have we got? -5 plus, what is that, 4 up there for x2 divided by 2. And then we got what, -2. We got +3. Yeah, this is looking pretty good. All right, so we got -5 plus 4 is -1. Divided by 2 is -1/2. And we've got that right there is +1/2. So we have verified that both of these diagonals are bisected, and because they share the exact same midpoint. Okay, so that's the proof that we did there. So we focused on the midpoint down here with the parallelogram, and we focused on the distance formula up here with the rectangle. And that's what we're really wanting to do in this unit. Again, it can get a lot more complicated than this, but we just want to keep it as simple as possible. Thanks.